Nuclear submarines are at the pinnacle of modern marine warfare and represent a powerful deterrent force. A silent, invisible hunter, like the Sea Wolf class, USS Jimmy Carter, that can attack surface ships with torpedoes and land-based targets with missiles. The design and engineering behind these monuments have been closely guarded secrets from the beginning of their construction. The first submarine was created during the American War of Independence by the Americans in order to plant bombs below the waterline of British ships. This turtle was just a sealed barrel with barely enough room for one man, which he could steer just enough to reach his targets. From the early days of tanks to the modern warfare of today, the designs of these machines have come a long way. Below, we list 10 design features of nuclear submarines that have declassified over time. Number 10. Electric torpedoes. Early torpedoes used compressed air to drive them through the water. But the line of air bubbles they produced easily revealed their presence to vessels on the surface, making them easy to avoid. During World War II, Germany developed battery-operated torpedoes that used an electric motor for propulsion. The last electric torpedoes, the Mark 24 Tigerfish, carried on board Royal Navy submarines, used maintenance-free silver oxide batteries instead of the earlier lead-acid batteries. These improved batteries could be stored for years without loss of performance, reducing their total life cycle cost. Number 9. Depth control. The captains of the first submarines controlled their depth by pumping water in and out of the ballast water tanks. That crude system has been replaced with fins that look like small wings that can tilt up and down. There are two sets on a modern sub: the fair water planes, a mid-shift, and the stern planes at the aft, or back end. The fair water planes create hydrodynamic forces to steer the sub up or down in a water column. The stern planes are like the elevators on an airplane, controlling the angle that the nose of the sub tilts up or down. The planes are operated by junior officers training to stand watch at the helm, using electronic controls very much like the controls on modern aircraft. These operations are coordinated with crew activities, since they affect the angle of tables and the floors on which crew are walking. Number 8. Electrolysis Air System. The first hurdle to underwater operation was to provide a breathable atmosphere. That's over 12 cubic meters of air per crew member per day. To carry air in pressurized canisters severely limits the distance or range of a submarine. So instead, on nuclear submarines, pressurized canisters have been replaced with a system that generates oxygen from the very seawater through which the submarine flies. Applying an electric current through seawater splits the water molecules, or H2O, into hydrogen and oxygen. Flammable hydrogen is stored until it can be vented safely outside the hull, while the oxygen is circulated throughout the vessel. The oxygen generator system on a modern submarine produces as much as 4,000 liters of oxygen every hour, regulated with sensors to maintain safe breathing levels. Since the nuclear power plant supplies nearly unlimited electricity, this system gives the sub a nearly unlimited range. Number 7. Remote-controlled and programmable torpedoes. One limitation of electric torpedoes is controlling them. Essentially, they continue in the direction they are launched. Once they are detected, they can be avoided simply by moving out of the way. It's time to up the ante by developing a steerable torpedo, instead of releasing the torpedo with a single command. Remote-controlled and programmable torpedoes, like the MK-48 ATCP advanced capabilities currently deployed with the Ohio-class nuclear submarines, have a fiber optic cable that transmits commands from the operator instantaneously, so it is guided until its target is in sight. They also carry their own guidance system that is pre-programmed with the latest information on the target before they're launched. In the heart of the sub is the command module, which houses the torpedo control system. Crew track a target using onboard sensors and electronics to calculate the distance, direction, and relative speed between the sub and the target. The result, called the firing solution, is communicated to the torpedo in the bomb shop and loaded into its computer system. Then the torpedo is launched from the sub and steers its way based on its internal program. Number 6. Nuclear reactor. All of the systems on board the submarine draw power. Conventional submarines rely on diesel engines, which require refueling and release exhaust gases that give away their position. In 1954, the first nuclear submarine, the U.S. Nautilus, was launched, harnessing the power of the atom with only 4 kilograms of uranium. This sub could travel 100,000 kilometers underwater. Breaking atoms releases heat which is captured by a cooling fluid, which in turn powers a steam generator. The steam generator produces electricity for propulsion and all the crew operations, or hotel load. This breakthrough eliminated refueling at sea. Now, a modern nuclear submarine like the Ohio-class U.S. Pennsylvania can provide enough power to run a small city with a range limited only by perishables like food for the crew instead of air or fuel. Number 5. Steam-driven vertical launch missiles. During the Cold War, the Russians got the upper hand with the ability to fire nuclear weapons from submarines. This dangerous development opened up the theater of war from sea to land-based targets. Early systems require that the submarine surface to launch the rocket into the atmosphere, putting the submarine at risk. The race was on to find a way to launch a rocket vertically while underwater. Rockets burn fuel, so they require oxygen to launch them underwater. A compressed air system was developed. The rockets are housed in sealed tubes. Just before launch, a valve opens, releasing compressed air into the tube and pressurizing it. The seal is broken, and the pressure drives the rocket through the water at over 80 kilometers per hour, overcoming the drag of the water. Once it breaks the surface, the rocket engine can ignite and propel it through the air to its target. Number 4. Passive and active sonar. Hiding underwater, the submarine is hidden from view, but not entirely undetectable. Sound is their enemy where light doesn't penetrate. The speed of sound in water is 1,500 meters per second or 5,400 kilometers per hour, over 4 times the speed of sound in air. So it can travel great distances without loss in decibels or relative volume. Early submarines were flying blind when they submerged below the depth that light penetrates. Today, by using sensitive listening devices, the sonar operator can gather intelligence about surface and subsurface vessels and the environment are on the sub for navigation. Passive sonar is a system housed in the nose of the submarine that detects sound using a sensitive speaker. It can identify and distinguish between the sound signatures of vessels, whales, and seismic events from 1,000 kilometers without revealing the location of the listener. To navigate safely, the operator also needs to know the location of solid objects, like rock outcrops, underwater structures, and other submarines that may be standing still in the water. Active sonar detects solid objects by sending pings and measuring the time until the ping is heard, reflecting off the object and returning to the listener. Using the speed of sound in water, the distance to an object can be calculated from the return time. The latest systems use a spherical array of hydrophones to distinguish the direction of the signal in 3 dimensions, sensing from any direction around the sub. Number 3. Silent running through isolation and hydrodynamics. Send sound travels underwater for great distances. The hum from a motor or the tick of a clock would give away the location of a submarine. As more sensitive sonar systems were developed, ways to silence sounds from the submarine were also invented. So every piece of machinery is isolated with rubber mounts or coiled springs to prevent the vibrations that make up machinery noise from being transmitted through the hull. The largest source of noise is the propulsion system. As the blade of the propeller turns through the water, they can generate bubbles. These bubbles appear when the tip of the blade exceeds the cavitation speed. At this speed, the hydrodynamic lift generated by the blade produces areas of such low pressure that the water effectively boils. As the bubbles separate from the blade, they collapse with small implosions that are easily detected with passive sonar. Using advanced research in hydrodynamics, propellers are now designed with multiple blades, generating more power at lower speeds and eliminating cavitation noise. Number 2. Hull pressure chamber and hull tiles. The design of the hull has evolved from an oak shell held together with barrel hoops to a pressure vessel that can dive to more than 240 meters, where the pressure is equivalent to 25 atmospheres. The hull of a modern submarine is rolled from steel with curved ends and welded first inside and then out. Every weld is inspected using ultrasonics for defects to ensure it can withstand the repeated cycles it will experience as it dives and surfaces. The hull is not just a structure that protects its human cargo. On a nuclear submarine, the sheer size of the hull makes it an easy target to spot with active sonar. At 97 meters in length, the British Astute-class submarine is nearly as long as a soccer field. To hide it from active sonar, the hull is covered with a layer of rubber tiles that reduce reflection of sound waves. Number 1. Multi-mission platform Seawolf-class submarine. The Cold War drove the United States to design their most silent, fast attack submarine, the Seawolf. The hull is the first entirely made from HY100 high-pressure steel, a material that has achieved 360 meters in an unclassified submarine. Only 3 were built before the end of the Cold War, but these vessels have outclassed the Russian counterparts because of their versatility. In addition to transcending their predecessors in depth, speed, and stealth, the hull fits double the armament and launch capabilities with 8 tubes in berth for 50 Tomahawk missiles. Enter the USS Jimmy Carter, a variant of the Sea Wolf built 30 meters longer to accommodate its unique multi-mission platform. The MMP is an underwater hangar with a moon bay lockout chamber that allows it to launch autonomous and remote-operated vehicles and deploy cables and underwater sensors at depth. The Jimmy Carter is also fitted for an air-transportable dry deck shelter that piggybacks on the sub for storing and launching combat swimmers and a swimmer delivery vehicle, and it has a swimmer silo for deploying up to 8 fully equipped combat swimmers at a time. This vessel rivals Jules Verne's Nautilus of 20,000 leagues under the sea. The battle between nuclear submarine design advances continues, as each new technology defeats an old one. Revealed design secrets lead to advances in other sectors, from commercial shipping to personal watercraft. Do you know of any other submarine design secrets that have been declassified? Let me know in the comment section down below. Also, please be sure to like this video if you enjoyed it and subscribe, hitting that bell icon. Never miss another video. Thanks for watching.